Okay, so we're back on 5-4, solving by taking roots, and we're on the back side here. All right, so that is some terrible coloring on the board. Let's see if we can brighten it up. Okay, that doesn't look so yellow. All right, so we're taking roots allows us to solve some quadratics that can't be solved by factoring. And I think we kind of went over the example one to look at it a little bit. But we're going to isolate. To solve the quadratic by taking roots, we're going to isolate the squared expression. So the x squared, the c squared, the b squared, any of those. Apply the square root property and simplify the radical. So in example 3, we'll move that up a little bit. Okay, so this whole first part here is trying to get like adding 100, dividing by 3. Our whole goal was that first step was to isolate the squared expression. So we got it to x squared. Applying the square root property was that we did the square root of both sides. All right, and then we need to simplify. So we've got x equals a positive or a negative square root of 100 divided by 3.
Why do we write it like that and not just do 100 divided by 3?
Well, they kind of are all ugly. I mean, none of them are too fancy. But now the kicker here is that we have the square root and we have a fraction underneath it. So the square root applies to both of those. It's the same thing as the square root of 100 divided by the square root of 3. It's nice when we already know, like, right, the square root of 100 is 10. It's like, woohoo, that was simple. But we don't know the square root of 3, so it stays. Then the problem becomes we can't have the square root in the denominator. In order to have it simplified, there cannot be a radical in the denominator. So in order to get rid of that, we have to multiply by a number that's going to get rid of the square root. We know the square root, so like the square root of 2 times the square root of 2 equals 2. Right, whatever number is under that denominator, if it's multiplied by itself, it gives us the number, the whole number, without the square root. So no matter what it is. So in this case, we want to multiply this 10 divided by the square root of 3 times, okay, that's what I have here, the square root of 3 over the square root of 3. Because we also know any number over itself, right? 4 over 4 is equal to 1. The same way as the square root of 3 over the square root of 3 is equal to 1. So we're not changing anything. We're just moving the numbers around. That's how we can manipulate the numbers. If you divide it by 1, I multiplied by 1. What's it do? Okay, so what it does, that's a good question. We're going to have x equals the plus or minus, so we're going to have the positive and the negative, and we multiply the fractions. The numerator, 10 times the square root of 3, is just 10 times the square root of 3. And then, yeah, yes, if you want to call it that. Yeah, because then the square root of 3 times the square root of 3 just gives me a 3 in the denominator. But it's not a square root, it's a whole number. So this is final and simplified. It looks ugly, right? Doesn't look nice or neat. It's kind of an ugly number, but that is the simplified answer. Okay, so let's try the x squared minus 8 over here. Okay, so first thing we want to get our square by itself, our variable. So we're going to add 8, yes. So we're going to add 8. So then we would have x squared equals 8. That was a little bit easier. Then what? We take the square root of both sides. So the square root of x squared and the square root of 8. So I'm going to get x equals plus or minus. Anytime you take the square root, you can just write plus or minus. Make your life simpler. I would say, you mean, right, because 8 is equal to 2 times 2 times 2. We need a pair to pull out. So yeah, so this would be 2 times the square root of 2. And you're done. That one was it. Questions? Okay, let's look at example 4 then. We've got a little bit more work to do in example 4. Okay, so it says solve the quantity, or solve 4 times the quantity y minus 2 squared plus 6 equals 114. State the solutions as both simplified radical expressions, so that's simplified, okay, but they're telling you they're radical expressions. That means you're gonna have the square root in them. And as a solution set containing decimal approximations. So we want it as both. Yeah, when you put it in the calculator, it's going to give you a decimal approximation. Okay. All right, so let's start with our equation. So we've got 4 times the quantity y minus 2 squared plus 6 equals 114. Looks messy. Same first goal. Get the x, or get the part that's squared by itself. So how are we going to do that? Subtract 6. Awesome. So then I'm going to have 4 times the quantity y minus 2 squared equals 108. Then I divide by 4. Good. So then I would have the quantity y minus 2 squared equals 27. Oh, yeah, 27. Okay. Right, now I've got that squared. Perfect. So I'm going to change colors because I've got like, yeah, like step 1. I got my thing isolated with my square isolated.
The y minus 2 squared, isn't that like the same thing as what we did in the past, where it's like y plus 2 times y minus 2 or whatever?
It is, but we are doing it, we're not factoring it this time. We're solving it by taking the root. So since this quantity is squared, we want to take the square root of it, right? So if we take the square root of this, the square cancels the square root. So we're left with y, whoops, I almost put plus. Maybe. Okay, so we're left with y minus 2 equals plus or minus the square root of 27. Okay, so let's think about 27 if we can do the square root. So let's do some division by primes over here. It's not even, so I can't do 2. 3. Okay, 3, not 27 divided by 3 is 9. 9 divided by 3 is 3. Okay, so I have a pair of 3's. So this is going to be y minus 2 is equal to plus or minus 3. That I pulled out, and then times the square root of 3. Okay, now what? No, because it was inside the parentheses. This is right. Like the 2 was in the, this was inside the parentheses under the square root. So we should not have added it any earlier.
What about the step above it, though?
You could have added it at the step above, like here. Right here. You could have. That would have been okay. And then you would have simplified afterwards. That's okay. So then this is going to be y equals 2 plus or minus 3 times the square root of 3. But now you've got your variable all by itself. So this is that simplified radical expression. Check. We got that one. So now we need to do the decimal approximation. The decimal approximation. So like if you got your calculator and you put in 3 times the square root of 3, what do you get out?
A big number.
You don't actually get out a big number. kind of small.
It's a lot of numbers, but it's not necessarily big.
Oh, okay. I see. It is a lot of.
Syntax error, that's what I get.
If I could turn mine on. You got a syntax error?
Wait, hold on.
I mean, the calculator is only as smart as the operator.
Yeah, I put it in.
Okay.
5.19.
Do you have one? Or do you need one? Oh, in your bag. But you're being lazy. Okay. Being lazy on me? I see how it is. There we go. Okay, so yeah, when you get it out, because you really just put in like 3 times the square root, it gives you a parentheses. So you put in the 3 and then make sure you close your parentheses on your calculator. Okay?
You don't actually put the times button in.
Yeah, you don't actually put the times button in.
That's what I did.
Okay, so it's an approximation to the nearest hundredth. So we got 5, right? 0.19196. So that means I'm going to round it to 5.20. We don't want to put the 0, so they know it is still a hundredth. Here's something different. Yeah, you don't actually put the, because you do 3 times the square root. Oh, I just did it. Oh, did you do, oh, it's the cube root. That was the cube root. I did the same thing. I hit the wrong one. The cube root is up here. The square root's down here. And then the 3. Yeah, right? Okay, so then if we wrote this, if we replaced that, then we would have y equals 2 plus or minus 5.2. And actually, it's not 2. We would make these wavy lines because it is the approximation. But we simply replaced the radical with our decimal approximation. So it's only wanting to 1 decimal. 20. Sorry, hundredths we had, because it was 196. So we couldn't leave it at 19. We had to round up to 20. Hundredth is.
Oh, because it's 9, yeah.
Okay. And then it says, as a solution set that contains those. So my solution set is when I actually do that. So that's going to be y. When I do, yeah, 2 plus the 5.20. And y equals 2 minus the 5.20. What are my 2 values at those points? Okay, so because I have a plus and a minus, this is going to give me two x values. So when I do 2 plus 5.20, my y is going to be 7.20. Oh, and those can be negative. Yeah, when I do 2 minus, it's going to be negative 3.20. Yeah. So my final solution set would be, if we use set notation, the negative 3.20 and the 7.20. So this is when we have 2 very different numbers. Or I shouldn't say very different. They both have the 0.20. But instead of just ending with the plus or minus 3 times the square root of 3, because we have to add the positive 2 in there, we end up with 2 different looking numbers. We can't just go with a plus or minus. Says Galileo. I don't know, says who.
So if you were to take factors, would you get the same answer?
Do what?
If you were to do the factoring thing, would you come out with the same answer?
You would not be able to do the factoring way this way.
But if you...
Because look at the answers. The answers are not. Factoring only works when we have whole numbers, when our answers are whole numbers.
But if we did it when it was a whole number, you did them both, would you get the same answer?
Yes. Yes. If your answer, like there were some, like in the beginning on the front of the worksheet, I showed you one in class yesterday where you could do it either way and you would get the same answer. Yes. This is for really for when you look at it and you're like, I can't factor this. I can't do that in my mind with a trinomial. It's no longer a trinomial either. But yeah, when you look at it, you're like, well, I can't do this and figure out the factors that would sum to be those numbers.
Another question.
Yes.
Why can't you just solve for y?
Because the y is a squared value. And so you would have to, this is how you do solve for y. It's going to have two possible answers. I know, because when you square numbers, it ends up with weird things. I know, it's crazy, isn't it? It's true, because there's that positive or that negative in there. All right, so let's try, or the next sheet there. It says solving x squared plus 1 equals 0 by taking roots produces the following. Okay, so let's check this one out. So we subtracted 1 from both sides. So we got x squared equals -1. Well, then when we take the square root of both sides, we get x equals positive and negative square root of -1.
I'm sorry, I was dying.
Sure. Are you alive now? Okay. All right, so if we look at this problem, where we're solving x squared plus 1 equals 0, we subtract 1. So to isolate, we get x squared equals -1. We take the square root of both sides, gives us x equals positive or negative square root of -1.
Why?
Because we had a negative number there.
Why?
Right? It's not a real number.
But why?
It's true. So this is, we're getting into the imaginary world.
Now I wish I had died when I was joking.
Okay? So it's actually not too terrible. Okay? When we have the square root of a negative number, we're going to use an I because it's imaginary.
You're telling me they're like, wait, we can't do this, and somebody else was like, just make it up, and they're like, sure, and now they teach this in high school
and colleges worldwide.
This hurts my brain.
Okay. So an imaginary unit, or I.
I don't believe anything. It's like, yeah, you can't do that. Except for when you can. No,
it's true.
Do that unless you just make it up, and then it's okay.
Okay. So is the square root of -1. So I, if we look at that, right? So we've got I equals the square root of -1. Okay. I squared then is equal to -1.
So instead of just writing -1 or negative whatever, why do you replace it with a variable when you can just write the number as equal?
So it makes it a little bit easier if we just, like if we write the I. So you know that you automatically, when you look at the problem, you know it's going to have a negative. You don't forget it. So yeah, so instead of writing the plus or minus the square root of -1, we write plus or minus I is what you're going to see. Touche. Mm-hmm.
Why don't, like, with the x one up there, why don't we just, instead of taking it to the square root of -1, why don't we just stop there and then just leave it as x squared equals -1? That is a good point, because when we got there at the other problem, we left it like that. Yeah.
Well, but you're moving beyond that in math currently. And I don't, like, so I know that there are...
That's the point we need it, and then working backwards with the different
well, we're not working backwards yet. We're just learning how to write imaginary numbers. And there are real life applications to this. I just don't know of what, like, I can't think of an example, yes, where they actually use imaginary numbers. But at the same time, like, this problem is a valid problem, so it's not like the problem is imaginary. It's just taking the root is where we get into the imaginary number. So, but the cool thing about it is, like, if we look at this one, that's the square root of -9. We break that down and say, well, it's the square root of 9 times the square root of the -1, because we want to get rid of this negative under there. So it's the same thing as 3 times I. How? Because the square root of 9 is 3, and then the square root of -1 is the same thing as I. So it would be 3i. Okay, or when we have a longer one, when we're doing it, the square root of -12, this is not a perfect square. So we say, well, -1, and then times 2 times 2 times 3. We have the pair of 2, so we can pull those out. And then the square root of -1, we can also pull out because it's I. So we have I times 2 and then times the square root of 3, or 2I times the square root of 3 is our final answer. So numbers like this, I, 3I, and 2I times the square root of 3 are pure imaginary numbers. Because they have an I in them, you know, like, okay, I'm dealing with imaginary numbers. I'm dealing with a negative, a square root of a negative 1.
Where did you get negative?
It was just an example. These are just some examples. Yeah, it's a different problem. They're just example, like I just wanted to put some examples up there so you could see how it works. Okay. All right. Then if we look at the square root property, okay, so it says if x squared equals k, the square root property, k is greater than 0, then x has 2 real solutions. Okay, and it's going to be written as that plus or minus the square root of k. We've already done this. This is just putting it into like algebraic words or definitions. All right, if k equals 0, then there's one real solution, x equals 0. And if k is less than 0, we are going to have 2 complex solutions. So that's getting into those imaginary numbers. So like earlier we had the one that we've solved, we got down to the point where x squared equals negative 1. That's why our k, this was negative 1 is our k value here. It was less than 0. That's why it ended up with those 2 wonky solutions. Okay, it ended up with the I. So if we look, we're going to practice these. And they're both going to get us, we can see complex solutions here of what we should get. But it's the same goal. So m squared plus 45, we're going to subtract 45. I don't know what. Okay, and we get m squared equals negative 45. Then what do? The square root, because there's a square in it. So then m equals plus or minus the square root of negative 45. We're not, because it has the negative. And we have to simplify the radical. Right, we've got to simplify the radical. So here's the thing. If you see the negative in here, just bring the I out. Right? And then just treat it like a regular square root. So 45, let's do divided by 5 is what? No. No. Yeah, because once I have the negative, I can pull the I out and it's gone. Like I've taken care of the negative if I go ahead and take the I out of the radical. Because the square root of negative 1 equals I. Right, but if I say, well, the square root of negative 1 times the square root of a positive 45, well, this is I. Right, because the square root of negative 1 is I. So I pulled them apart and said, well, the square root of negative 1 times the square root of 45. So I could say, well, this is I, and now I can deal with the square root of 45 part. Because negative 1 times 45 is negative 45. Just like 1 times a positive 45 is a positive 45. But if we finish our division by primes, what would we divide mine by? 3? Okay. And we'd get 3. So, I mean, there's a couple different ways we could write it. We could write it as the square root of negative 1 times 5 times 3 times 3. All right. The square root of negative 1 comes out to be an I. I did. I'm just re-showing you a different way to look at it. So, like, if you're still confused, like, maybe this would help to see me, like, do it at a different way. And then I have a pair of 3's I can take out as a 3. And then I have to keep the 5 because there's only one. So it's 3i times the square root of 5, and then it was plus or minus. So m equals plus or minus 3i times the square root of 5. Okay, so we doing all right? Okay, let's try the next one. It's just the same process over and over and over again. Okay, so subtract 10. So we have 2 times the quantity w plus 3 squared equals negative 8. What do I do next? Divide by 2. So now I'm going to have w plus 3, probably that quantity squared, equals negative 4. All right, what's my next step? Take the square root. So now I'm going to have w plus 3 equals plus or minus the square root of negative 4. Okay. So w plus 3 equals plus or minus 2i. Then we subtract 3 from both sides. Negative 3. Yep. All right, Josh, you can go ahead and get started on your homework.
The stuff that's written on these.
Yeah, on the front. Okay. Brandon and Ethan. How are we doing? Where's your homework from yesterday while we're working on that? Okay, I'm going to go ahead and pause this, and then I'll answer questions if you guys, gentlemen, have them.